When I made my video on derivatives in sequence, I brought up this idea of finding a polynomial that generates any sequence. Now, exactly how to do that was a little ambiguous, so I am back to give the definitive method for figuring out what that polynomial is. So let's quickly review. If you take the difference between terms enough times, eventually you either get a constant or a single number. This is similar to some kind of polynomial of degree n whose nth row of differences will always be constant. So now we just need to figure out how to generate these polynomials. The easiest case would be to let the top of the pyramid be 1 and make as many other terms 0. Just this last diagonal is full of 1s, but that's something we can work with. If we suppose this is the nth row that was a constant, the original first row has n terms. Quick pause. For precision's sake, I'm going to refer to the sequence as the first row from here on out. Note that n rows of differences gives a polynomial of degree n, but with a total of n rows, we get a polynomial of degree n minus 1. Alright, let's get back to where we were. We have n minus 1 zeros, and if you know anything about polynomials, they give us almost everything we need to know. Since inputting 1, 2, 3, and everything else is 0, it tells us that x minus 1, x minus 2, and x minus 3, and so on are all factors of our polynomial. We have n minus 1 of these zeros, so putting them together immediately makes our n minus 1 degree polynomial. Except, well, not quite. In addition to all the zeros, we still have a constant term to determine, which is where we use the last number 1. This tells us that evaluated at n, our expression should give us 1. With the factors we have so far, we would get n minus 1 times n minus 2 down to 1, or n minus 1 factorial, so to make this 1, we just divide the entire thing by n minus 1 factorial. And with that, we're basically done. All we need to do for a sequence is to generate the differences, check the diagonal for the first terms of every row, and generate the corresponding polynomial for the degree with 1 multiplied by the diagonal term. Summed all together, the core first diagonal is preserved, and the original sequence can cascade down as you solve for the rest of the terms. What's really cool is that each polynomial we had earlier leaves a pyramid frame of zeros that is effectively an empty canvas for another polynomial to adjust. They divide and conquer to slowly chip away, and they give us this pretty formulaic way of solving sequences with polynomials. Now, let's run through an example with the nice polynomial of 2x cubed minus 4x squared plus 3x plus 2 that I've used before. It generates a sequence 3, 8, 29, 78, and 167 with differences that go up with 5, 21, 49, 89, 16, 28, 40, and then a constant 12. The terms we will care about are 12, 16, 5, and 3. With 12, we take the corresponding 3-degree polynomial x minus 1, x minus 2, x minus 3 divided by 3 factorial times 12. For 16, we take the 2-degree polynomial x minus 1 times x minus 2 divided by 2 factorial and multiply it by 16. And the last two follow with 5 multiplied by x minus 1, and 3 is just 3. Now, there are two ways of going about adding all of these up. One of them is to expand them all and add. If we do that, we get 2x cubed minus 12x squared plus 22x minus 12, 8x squared minus 24x plus 16, 5x minus 5, and 3. Summing the four expressions together gives the original 2x cubed minus 4x squared plus 3x plus 2 that we started with. However, this has a long list of equations where we can easily make silly mistakes. Another option we have is a more iterative strategy. Each polynomial we add on adds an extra x minus term and increases the denominators by dividing by that term. With this knowledge, we can actually factor to make this operation easier. Factored out properly, it will look somewhat of a messy equation like this. Starting from the middle, we can expand x minus 3 over 3 out and multiply it by 12 to get 4x minus 12. Add on the next 16 to get 4x plus 4. Now we want to pull out x minus 2 over 2 to get 2x squared minus 2x minus 4. Add on the next 5 to get 2x squared minus 2x plus 1. Then multiply by the last x minus 1 to get 2x cubed minus 4x squared plus 3x minus 1. And with the last step, we want to add 3 to get 2x cubed minus 4x squared plus 3x plus 2, the original equation. Step by step, everything gets eliminated and any old sequence becomes solved by a polynomial. And if you're cool with linear algebra, it's all a bunch of matrices, but that might be a story for another day.